Okay, welcome everyone to our weekly ITC lunch. Today after lunch at 2 p.m. everyone is invited. There is an event at the library, the lower level of the Wallbach Library, and it's a celebration of the interface between science and art, and a new sculpture that is being donated about Galileo. Between 2 and 3 p.m. We will have the sculptor there, and also a musical performance and a short presentation by a professor of the history of science, who happens to be married to an astrophysicist. Her name is Hannah Marcus, and her husband's name is Morgan McLeod. He's not here. He's on travel, but we will hear from her an overview about Galileo's life and research. She has a new book coming on this subject. And so everyone is invited if you want to learn more about Galileo and the art that accompanies it. Otherwise, we have 4 presentations today, and just a reminder, we don't have the colloquium because of the large number of talks that are with all the prospective junior faculty on both the Smithsonian and Harvard sites. Hopefully in March we will renew the colloquium. So today we will hear from Scott Lucchini, who actually is involved in organizing these luncheons, so we are grateful for your help in that. And he agreed to speak as well on the subject of high-velocity clouds and galaxy evolution with TNG 50. And then we'll hear from Dan Patnaude. Where is Dan? Over there. He was supposed to speak a couple of weeks ago, but didn't feel very well. But we are very glad to have him. He will talk about the 3-dimensional structure of the young core collapse supernova G292 plus 1.8. And then we'll hear from Gokul, okay, that's a challenge, Srinivasaragavan. You can probably say it better. From the University of Maryland in College Park, who will tell us about multi-wavelength analysis of a Luminous Orphan Afterglow with evidence for a structured jet. And finally, we'll hear from our own Cassie Locas, who is also helping us with organizing the talks here. And she will speak about circumgalactic emission affected by star formation feedback. Go ahead, Scott.
Okie dokie. Hello. Hi, everybody. I'm Scott Lucchini. I'm a postdoc here at the ITC. And today I'm going to talk about the circumgalactic medium, some of my recent work on high-velocity clouds with the illustrious TNG simulations, looking at the circumgalactic medium and how we can learn more about our own Milky Way by studying these simulations. And so here it is. This is our Milky Way. This is a map of high-velocity neutral hydrogen around our galaxy. And so we've taken the Hi4Pi survey and subtracted all of the gas that's co-moving with the disk. So this is only the gas that remains that's at high velocities relative to disk rotation, and it traces the inner CGM and the disk halo interface. Some of it, obviously, is external galaxies, the Magellanic Clouds, M31, M33, and the stream's a bit of a special case. But most of this is the inner CGM of our own galaxy. And while we've done a little bit of absorption spectroscopy to constrain their distances and to learn about the composition of these clouds, we really don't know much about the origins and much of the properties because they're difficult to observe. So this is where illustrious TNG comes in. This is the galaxy from that title slide as well, 537941 in TNG 50 for anybody familiar. It's a Milky Way mass galaxy, and we took the snapshot at about redshift 0.25, identified all of the cold cloud structures in the circumgalactic medium at that time, compared their velocities to the disk rotation within the simulation, and isolated those that would be observable at high velocities. So we have a sample of high velocity cloud analogs in this simulation, and then we traced them backwards in time to redshift 0.5 to see where they came from, to learn about the origins of these structures. So this is our sample. Here's a projection of all the gas in this galaxy at redshift 0.25. The solid line's the virial radius, and the dashed line's the extent of our search for these cold clouds. And these gray regions are HVC analogs. You can see that there's more in the south than the north, but they're mostly within 50 kiloparsecs, and there's a whole variety of morphologies, large ones, small ones, filamentary ones, blobby ones. So we see quite a range, which is interesting. And then we took these clouds, tracked them backwards. Oh, nope, we didn't do that yet. First, we got to look at what this looks like from Earth, because obviously we don't have this view of the Milky Way. We want to compare apples to apples. And so we looked at an all-sky projection of neutral hydrogen from within this simulation. So I put the view from a solar-like position, projected the neutral hydrogen, and this is what we get. The white outlines are the locations of our high-velocity cloud analogs. So there's a bunch of gas along the mid-plane here. That's due to the warp of the disk, and so we excluded that from our high-velocity clouds. But the rest of it overlaps pretty well. We've got a whole bunch of clouds that agree with the detections in neutral hydrogen. And then, now, we trace them backwards in time. And so here is an example for one cloud. We have 6 different properties. For a single cloud, we identified it here on the right of each of these plots at redshift 0.25. And we track its properties backwards in time to redshift 0.5 to see where it came from. So we have galactocentric radius, distance from a detected subhalo, see if it's from a satellite, radial velocity, orbital diskiness, so this compares the angular momentum of the motion of the HVC to the angular momentum of the disk, temperature, and cooling time to freefall time ratio. We then take the initial values for these 3 properties, the maximum values for these 3 properties, and we have 6 numbers for every HVC. And using these 6 numbers, we can determine where it came from. So high-velocity clouds that started out within the disk, originated from the disk of this galaxy, must have started close with a low value for initial galactocentric radius, with positive radial velocity if it's an outflow, or angular momentum aligned with the disk if it's still within the disk before being thrown out. Then anything that's far away from the central galaxy and close to a subhalo, that must have originated from a satellite, and everything that's left formed out of the circumgalactic medium itself via thermal instability. And so based on the maximum temperature that these clouds reach, whether they hit warm temperatures or hot temperatures, we classify them in 2 categories, and we confirm that all of them have cooling time to freefall time ratios less than 10. So the changes in temperature that we see can be due to the radiative cooling that's going on. And so this is the distribution that we end up with. By number, the majority of clouds are formed via thermal instability out of the CGM, with some contribution from the disk and the satellites as well. But if we look at the distributions based on mass, the satellite contribute a lot more. So these satellite origin high-velocity clouds are the bigger ones. They're more massive ones that are dominating here. But we want to compare this to the Milky Way. We want to bring this back to our observables. And so we now look at observable properties of these HVC analogs classified by their different origins. So here's the projection on the sky, the galactocentric radius, metallicity, and radial velocity. And so as expected, these disk origin high-velocity clouds can have higher metallicities than average, and they have positive radial velocities. The satellite origin ones have low metallicities, which is interesting. They seem to be the only ones that are able to reproduce this very, very low metallicities. And we think that's because they're larger, they're more protected from the strong mixing that goes on as they pass through the circumgalactic medium. The ambient CGM's at about 0.1 solar, which we can see from the thermal instability clouds, but these ones would have lower metallicities and are more protected as they move through there. And then the thermal instability clouds are infalling at a wide range of galactocentric radii. But we know this isn't the full picture. High-velocity clouds are multi-phase. Around the Milky Way, observations of absorption line spectroscopy have shown us that. So here's some data from Philip Richter's paper in 2017. Here's 3 different sight lines towards high-velocity clouds and a whole bunch of spectra for each sight line. Down at the bottom is the H1 emission, probably easiest to see in this one. The blue region is the velocity range of the high-velocity cloud. And we see absorption carbon-2, a little bit in silicon-4, silicon-2, silicon-2, along those same velocities. For all of these different sight lines, we see multi-phase gas moving at the same velocity as these clouds. But what do we see in the simulation? We can do a similar thing using Trident to make mock absorption profile spectra along these lines of sight. We see emission in H1 that we can see in this all-sky map, but then also co-moving absorption along a whole bunch of different ions along each of these different lines of sight. And so we do seem to reproduce the observations with these HVC analogs. But again, simulations are great. We can go the next step further and say, well, what does this gas actually look like? From the observations, we know it's moving at the same velocity. It's along the same line of sight. But now we can say, well, what does it actually look like in 3D space? And so here are the neutral HVCs in blue for the 3 clouds I showed on the previous slide, and the ionized gas that's co-moving with the HVCs in red. This is the galactic disk for scale. And we see some head-tail structure. We see some complicated morphologies. But this is all of the gas that's co-moving with these high-velocity clouds. We can do this for all 70 of our HVCs. Supposedly, there's a background showing the total gas density. But in any case, there's a lot of the volume of the circumgalactic medium around this galaxy is occupied by these ionized envelopes. And so it is a dominant contribution to the total gas that we're seeing around this galaxy. In order to characterize it a little bit better, we defined a half size for each of these HVC envelopes, these ionized components of the HVCs. So basically, how far away from the neutral HVC do you have to go until the gas is no longer aligned in velocity, until we don't have co-moving gas anymore? And the median size is about 6 kiloparsecs. There's slight differences based on the origin pathway for these HVCs, but we're not sure how much of a dependence this has on resolution, so we're still looking into it. And then within this half size, we can sum up all the mass that's moving in that same direction. And we get a mass in the ionized component of the HVC, and we can compare that with a mass in the neutral HVC that we would see in H1. These lines are 1 to 1 and 10 to 1, and we see that on average, the HVCs have about 6 times more ionized gas in their mass than in the neutral component. And so these clouds are dominated by ionized material. In the final step, we compared this one result from the single galaxy that we've been looking at with 47 other Milky Way-like galaxies from TNG 50. This is from Vadim's sample that he published last year. And now each of these dots is not a single HVC, but it's a single galaxy. We've summed up all of the mass in the ionized component and in the neutral component for each of these galaxies and converted it into an accretion rate. So how is this gas going to affect the central galaxy? And so this is the accretion rate from the ionized HVCs compared with the accretion rate for the neutral HVCs. And there's a slope of about 3. So the ionized component still dominates, even in accretion, as well as total mass. We can compare with the star formation rates of these different galaxies as well, and we see trends with, again, the ionized accretion rate scaling with a slope of about 1 with the star formation rate. Here's showing this in another way, looking at the ratio of the accretion rate to the star formation rate in a distribution. And so the big result here is that it seems like while neutral high-velocity clouds can only could only balance about 10% of the star formation in the galaxies, the ionized component can get a lot closer to 100% to sustain the growth of these galaxies over time and refuel their disks. And so I'll put up, oh yeah, consistent with the observations. There were some back-of-the-envelope calculations done in these papers from the absorption spectra that seem to agree. Here are some plots and movies as a conclusion, and I am working on new simulations with higher refinement in the CGM to get a closer look at some of these structures and the details, so stay tuned for that. Thanks so much.
This is beautiful. But in terms of the underlying physics, the virial temperature of the halo of the Milky Way is about 1 million degrees, right? So it's much hotter than this object.
Right.
And then the question is, what about thermal conduction? Because if there was heat flowing from the hot gas to those, it would have evaporated them very quickly. So I guess you're assuming that they somehow managed to block the heat transfer, right?
Yeah, so there actually was a recent study looking at sort of isolated wind tunnel simulations, including thermal conduction and not, to see how cold clouds survive in a hot wind. And they saw that there wasn't that much of a role played by thermal conduction because the turbulence and the mixing and the radiative cooling plays the majority of the role in sustaining these cold clouds. As they're passing through the hot CGM, the boundary layers become very turbulent, and that warm gas that mixes between the cold cloud and the hot medium cools very quickly, and it can condense, and then the turbulent mixing layer continues to grow and cool and grow and cool, and so that's how these clouds can survive. Even though the gas itself in that cloud isn't the same gas that it started with, it's continually recycling and regrowing as it moves through the CGM. And so I haven't explored thermal conduction specifically, but there are some indications that maybe it's not the dominant process.
Okay, Lisa?
Yeah, my question is vaguely related to Avi's, which is when you're saying that this ionized gas can feed star formation, ongoing growth of the gas. How does that actually happen? Like, how does this gas actually get into space? Yeah.
We don't know. So this is the first step that we did here was to compare quantities, right? It seems like the amount of gas that's out there balances with the amount of gas that we need. And so in future work, we've tracked these HVCs backwards in time. Now we're tracking them forward in time to see, like, well, what actually happens. Because yes, this ionized mass, it's not ready to form stars, right? It's hot, it's diffuse, it needs to cool and condense and survive to make it all the way to disk to continue to fuel the galaxy. And so that is a big unknown still, yeah.
Jesse?
Are these clouds, on average, more like sweet potatoes or pancakes?
I think sweet potatoes. There are...
Why sweet?
Yeah, I think sweet potatoes are generally longer, right? But they... Oh, sorry, this thing is very loud. I think I have... Oh yeah, here we go. So we did look at the morphology of these ionized envelopes using this parameter T calculated from the moment of inertia tensor. And so it seems like the majority are prolate, and there's very few oblate envelopes. So they seem to align along filaments as these clouds are moving very fast through the CGM. So
People talked about over the past decade, where
right.
gas flows into galaxies along filaments. Are these the filaments that people were talking about?
I'm not sure. I think that in the past we've talked about filaments as these continuous cold structures, whereas this is ionized gas. But it could be coexisting in sort of mixing with these cold filaments and these ionized gas moving along with it. I think we might hear some more about this from Cassie in a couple minutes, but yeah, we'll see. Thank you.
Okay. Good afternoon. I'm going to talk to you now about the three-dimensional structure of galactic supernova remnant G292. I should say that this is work that's been sponsored by a Smithsonian Scholarly Studies Award, so I have to give the shout out to them. And a lot of this work was done by our two summer students who worked with Dan Milosavich at Purdue University. So why we would study supernova remnants in general versus supernova when we're interested in, say, the explosion properties of a supernova. We do know that from models that supernova are intrinsically asymmetrical. This is due to neutrino heating and hydrodynamic instabilities. And we actually can see some of these asymmetries if we look at multi-epoch observations of supernova. But this can be very difficult. Let's see if I can do this. Okay, well, so for instance, if you look at a nearby supernova remnant, supernova like 1996 CR, and you just look at the evolution of the oxygen lines, you actually see structure forming in the red and the blue shifted components of each of these lines. And this structure actually is reflective of the asymmetry that's in the expanding debris field. But we also know, if we look at, say, oxygen versus the products of oxygen burning, that this asymmetric nature is not fully formed. That is to say that there's actually a difference between the different layers of the ejecta. And you can see that in this lower plot here, where the oxygen emission is clearly separated from emission from things like sulfur and argon. And this says that while this was an asymmetric explosion, the turbulence wasn't so great that it brought about full mixing within the ejecta. But this is great, but we can't really do this for a large number of objects. There's only a handful of objects that we can do this regularly, and they have to be nearby, and they have to be sufficiently bright. So the next best thing that we can do, of course, is go to our own galaxy and look at supernova remnants. So this has been done for a few cases, notably Cassiopeia A, and recently the Crab, and some other objects in the Magellanic Clouds. But this is a Cas A analog. It's called G292.0 plus 1.8. It's much older than Cas A. It's 2,000 years old. This is what it looks like in the optical. I just want to make sure I guess this doesn't have a laser pointer on it. Oh, there it is. Oh, great. So this is what it looks like in the optical. This is oxygen 3 emission, so you can see that it's highly asymmetric. There's a neutron star with a high kick velocity. We studied it a few years ago. It's got a kick velocity of around 600 kilometers per second, which is quite high when you look at the distribution of neutron star kicks in the galaxy. And the neutron star is sort of located right about here, and it's traveling sort of in this direction, which is in the same direction as most of the oxygen emission. This would lead a theorist to suggest that you have some sort of tugboat mechanism that's pulling the neutron star along. In the X-ray, it looks quite different. This is what it looks like with a Chandra image. The coloring here is blue is sort of high energy emission. You can see the pulsar and its wind nebula right there at the center. The center of expansion is right here, so you can see that this is quite offset. There's a reverse shock, which we estimate to be right about here. And then there's shocked ejecta, so this is mostly silicon and sulfur, silicon and sulfur, argon, and the like. It's quite hard to do reconstructions of supernova remnants in the X-ray because we don't have the spectral resolution with silicon-based detectors. And if you want to do dispersive X-ray spectroscopy, you can kind of imagine what something like this would look like when you stuck it through a grating. But it has been done by this group here, Bolero, and they measured a number of knots. They found velocities of order 2,000 kilometers per second across the remnant, but this is only a handful of knots. So what we did, we started this during the pandemic, was we decided to start mapping G292 in the optical. We used, granted a significant amount of time on BADA to do this. This is very slow. We didn't have an IFU, so it was just basically take a spectrum step, over and over again. And as you can see, we've covered just about the entirety of the remnant. We have a little bit left to do right here, which will actually be done tomorrow night. And then this is why you shouldn't send an X-ray astronomer to do an optical astronomer's job. You know, we're going to go back and get that too. So, and that's probably the highest velocity stuff. So like I said, we have about 2 nights remain. We just mapped in this east-west direction. One thing you can note, you can see when you compare the optical emission to the X-ray emission is that the X-ray extent is much larger. This is a little bit different than other remnants. Typically, like for Cas A, for instance, the X-ray and the optical more or less are co-aligned, but that's not the case here. So just a typical spectrum looks like this. Nothing special. There's these fast-moving knots of ejecta. This is what we're interested in measuring. So we're measuring the oxygen 3-line profiles. You can see as you go in the cross-dispersion direction for something like this, you see both blue-shifted and red-shifted emission as you go up in the north-south direction of the remnant. And of course, just for sanity's sake, we actually see these so-called quasi-stationary flocculi, which is just circumstellar material that has been overrun by the shock, and now it's being lit up. But it's definitely circumstellar material. Okay, so what does this look like? We measure velocities around plus or minus 1,200 kilometers per second. And you can see that the first thing you notice is that there's this incredible pancake-like structure to the remnant. It's not spherically symmetric. One thing to note is that there's actually a circumstellar bar that sort of runs in the east-west direction. You see it in the X-ray. But it's really notable here how flattened this object is. And this isn't just because we missed stuff. This really is how it looks. It's not circular, or it's not spherical. And this actually turns out to be fairly common. So this is how it compares relative to the X-ray. Again, you can see that we don't get all the way out to the end of the X-ray emission, but there will be some optical emission out here as well. And then when you deproject it into sort of a Mercator projection, what you actually notice is that we start to see these rings and cavities that form. The thought here is that this is actually a relic of nickel bubble heating. So you form nickel-56 during the explosion. It heats up the surrounding ejecta, and then it eventually becomes optically thin to the gamma rays from that decay. And then you're left with these cavities, and you see all the stuff that bubble blew out and form the cavity wall, and that's usually stuff like oxygen and other objects and other elements, excuse me. But you start to see now these cavities sort of in one right here, there's another one over here, and then there's sort of these larger cavities as well. And this is something else that we see in younger remnants such as Cass A and 1987A.
Can you just clarify when you say 3D, how do you dimension?
Okay, so we're measuring the redshift of the line here. So then we assume some projection, and we can take that and actually position it along the line of sight.
So some kind of Hubble flow?
Yeah. You have to make some assumption about sort of how to convert that into that third dimension based upon the velocity. So. And then if you just look at how the X-ray, how the optical emission compares to, say, the direction of the kick of the neutron star. The neutron star is moving in this sort of down to the southwest, northeast, southwest direction. Sorry, it's moving down to the south. This is not the best thing. But you can actually see that it's sort of aligned with where there's no optical emission. So that suggests that the neutron star is sort of moving through these larger cavities within the remnant. So lastly, just how this compares to, say, other objects. This is how we see Cass A, and then an object called N132D. This is just the X, Y, and Z velocities for all of the ejecta knots that we measure. You can see that again, there's sort of this flattened distribution of the ejecta in this velocity space. And what this actually suggests is this is something that's inherent to the explosion mechanism itself, and not necessarily to any measurement issues that we're having. So I'll just stop there and leave out my slides here. And thank you.
So then that makes a lot of sense, the 3D approach that you're taking, because it happened that the explosion took place at a particular time, at a point, let's say, and then the distance that any fluid element reaches from the center is proportional to its velocity. Just
right.
Like the Big Bang.
Right, except that you don't immediately go to sort of a Hubble flow when you have an explosion, right? You have to, it's a couple shock doubling times before you reach that homologous expansion.
Yeah. Pressure doesn't play a role. If it's just free motion, then it is Hubble.
Yeah.
Okay. Thank you. Please.
Actually, I have the same question that you were asking. How do you know that this shape that you're getting is not instead the fact that the velocity field is not isotropic? Because it's kind of weird that on the plane of the sky, at least in X-rays, it looks very spherical.
Yeah.
But you get this very...
You get this very pancake distribution, right? So, so there's the inherent assumption that we have to make some assumption when we do that deep projection. And the student who did this, he chose a range of parameters in order to actually do the reconstruction, and he always arrives at that same shape. So it's not like picking just one. I'm just going to assume spherical symmetry and go from there. He's actually assuming various different initial conditions in order to actually get that reconstruction, and this is what he arrives at in general. So yeah.
Alexia?
How much do you know about what's around this particular supernova and whether or not that matters in terms of density gradients?
Yeah, so we actually, the density, except at least from X-ray observations, suggests that it was it's expanding into sort of a red supergiant wind that's fairly isotropic. Now we do know that there was a circumstellar bar, so that indicates that there's axial symmetry along the north-south axis. So I don't know how to describe it, but like the bar runs east to west, and so if you just imagine something exploding in like that, you actually are going to get some sort of bipolar explosion that's driven a little bit by the circumstellar environment. We see that in some supernova as well, but this is now 2,000 years old, so it's actually ran through much of that circumstellar environment, and the imprint of that interaction remains on the X-ray and the optical emission. So we can't unfortunately unfold that, but this does capture, at least if we at least assume that everything is moving radially, right? This still does capture the coherent structure that underlies how the ejecta is expanding.
How big is the whole thing?
It's about 8 arc minutes in diameter.
No, in parts.
Oh, can't do that in my head. So,
Yeah, it's probably, because I mean, that's big enough that the structure of the interstellar medium matters.
it's definitely near the edge of where the sort of the red supergiant phase began, so out about several parsecs away. And it's sort of moving now into the wind from the main sequence progenitor. So I don't think we're all the way out into the ISM yet, but we're certainly at the outer part of the red supergiant wind.
So this supernova took place when Jesus was born? Is that...
We didn't actually see it. So in this paper by Long, we actually did do a historical study, and nobody actually observed it. It was too far south for any European nations to see it, and not the best time for them to be looking anyway. And the Chinese didn't observe it as well. So.
By the way, about 3 decades ago, there was a discussion about these bullets that are seen in X-rays of very fast ejecta. Do you see any evidence?
In this object, no, we don't. I mean, we see it in other places. I think you're thinking about the bullets in Vela.
Right.
They're actually not that fast. They're like a few hundred kilometers per second. But the stuff here is moving maybe an order of magnitude faster than that. But we don't see individual knots of ejecta in the X-ray here. So.
There are no more questions. Let's thank them.
Hello. Okay. Hi, everyone. My name is Gokul, and I'm really excited to be here to talk about Orphan Afterglows, AT 2023 SVA, and the state of the field. I actually sent over a different title, so sorry that it didn't go through. I changed it up a little bit because I didn't want to just focus on AT 2023 SVA. I wanted to talk a little bit more about the context of orphan afterglows in general and kind of place AT 2023 SVA in the context of the overall field. So in this talk, I'm going to be trying to answer these three main questions. What are orphan afterglows and their importance? What is the overall state of the field? And what conclusions can be drawn from our study on AT 2023 SVA? So before I talk about orphan afterglows in particular, I need to talk a little bit about long gamma ray burst science. Now, long gamma ray bursts are short-lived flashes of gamma ray photons that are released from highly collimated, ultrarelativistic jets, driven by compact object central engines left behind after core collapse supernovae explosions. This is a really nice figure from Zaros and Rees that shows the emission mechanisms of GRBs, and it's mainly divided into two different parts. We have the initial prompt emission, which arises from internal shocks within the jet's ejecta at early times, which produces gamma rays on the order of around seconds, and eventually the relativistic jet begins to slow down, interact with the surrounding medium, and produces the afterglow, which can last from weeks to months after the initial prompt emission, and it lights up the entire electromagnetic spectrum. So how exactly do we do GRB science? Well, usually we start with high-energy satellites, such as Swift, BAT, or Fermi, that detect high-energy gamma ray emission from some source in the sky, and they're able to localize it to some degree localization. After that, telescopes like Swift's X-ray telescope are able to localize the X-ray afterglow to arc-second precision. Then we utilize optical telescopes to follow up the source from the ground, get a redshift measurement, confirm the fact that it is an optical afterglow corresponding to the high-energy source that was found by the high-energy satellites, and then undergo GRB studies. And then we utilize radio telescopes to track the evolution over months to try to constrain some of the important jet properties. So that's the story for how long GRB science works in general, but orphan afterglows, on the other hand, are afterglows that are found serendipitously without the use of a GRB trigger in the ultraviolet, optical, and infrared wavelengths. This has been made possible by the advent of new transient surveys like ZTF and ATLAS. Now, in certain cases to an afterglow discovery, if we go back and we actually look at the gamma ray burst archives, we do see that there was associated gamma ray emission at the same spatial and temporal location of the afterglow discovery. But for some reason, it might not just have been triggered due to the fact that the localization was poor, or maybe it was a sub-threshold detection. But in certain cases, only a few, when we go back and look at the GRB archives, we actually don't see any associated gamma ray emission present at the time of the afterglow discovery, even when we have high-energy satellites that are pointing at that location in the sky. And these are what are known as orphan afterglows. But what physically are they? The truth is we don't really know. Here's a really nice schematic from Anna Ho that shows some different scenarios for what could produce an orphan afterglow. We might have a off-axis jet where initially, because of relativistic beaming effects, we can only see GRB emission within a viewing angle of 1 over gamma. And remember, for GRBs, gamma is around 100, so that viewing angle is very small. At later times, the relativistic beaming cone will widen, and we might be able to catch the afterglow. We could have a jet that is actually choked by its progenitor star or in a dense circumstellar medium environment due to very eruptive mass loss at the end of the progenitor star's life. Or we could have an intrinsic weak jet or dirty fireball with a low Lorentz factor. This could happen due to baryon loading, where we have a very baryon-loaded jet, and in this case, due to pair production processes, any gamma rays that are produced will get reprocessed to X-rays. And we might actually see this in an X-ray flash scenario. Or it could be something else altogether. So currently, there are only optical discoveries for orphan afterglows, but this is going to change in the future with future facilities like Ultrasat that's going to be able to detect them at the UV wavelengths. So now we know what orphan afterglows are, but why do we care about them? Well, they demonstrate that the gamma ray sky is not the only avenue to discover relativistic transients, and it opens up an entirely new discovery space for trying to find transients corresponding to this continuum of relativistic stellar explosions. Furthermore, if some orphan afterglows are actually off-axis jets, they can help us understand the true angular rate and structure of long GRB jets. Furthermore, if some of them are actually intrinsic dirty fireballs, they can help illuminate the role that mass loading plays in powering these ultra-relativistic systems. So this table from Maggie Lee's paper in 2024 shows a really nice state of the field for orphan afterglows. So currently, there are 10 orphan afterglows that have been reported thus far in the literature, and 6 of them had redshift measurements. And we can tell from the proposed models that there are a variety of different proposed models, and they're pretty much riddled with degeneracies. If you want to know why, ask me after the talk. So for the rest of this talk, I'll be focusing on AT 2023 SVA, and sort of the properties and the conclusions that we can derive from our multi-wavelength analysis of this source. So here were the proposed models that we find, and the one that we think is most likely is that it is a slightly off-axis structured jet with a classical GRB Lorentz factor. So what does that mean? Before I get into it, I'll give a little bit of context behind GRB jets in the literature. So usually in the literature, GRB jets are sort of defined as this top hat structure, which have a constant energy per viewing angle, no matter where we are with respect to the jet's axis. Outside of this top hat structure, the energy kind of drops down to 0. But there have been studies that show that some GRBs show significant evidence for having structure in their jets, or having angular energy profiles that actually evolve with respect to the angle of the jet's axis. Some of these GRBs include GRB 221009A, the brightest GRB of all time, GRB 170817A, the short GRB associated with the gravitational wave event, and other events like GRB 030329, which was studied extensively by Professor Ido Berger in this department here. So from our analysis and the multi-wavelength modeling that we did, utilizing the radio, X-ray, and optical observations, we find that the most likely scenario for AT2023 SVA is that we are viewing a power law structured jet, slightly off-axis, just outside of the core opening angle. And this is actually very similar to the jet model that was proposed for GRB 221009A, which is showed from this really nice schematic from Freeburn et al. 2024. So in this model, we have a very narrow core of the jet that has really high Lorentz factor moving material and produces gamma ray emission, if we are viewing it directly inside this core, which is defined by theta C. Then, as we extend out to theta W, we get into the wing of the jet, where in this case, the angular energy profile of the jet evolves as a power law, theta to the negative B, where B is some power law decay index. So if we're viewing the jet outside of the narrow core, but inside of the wing, we would actually be missing the prompt gamma ray emission, and we would see the event as an Orphan afterglow. And this is exactly what we're seeing from our event, according to our modeling, where we find that the best fit opening angle is around, the best fit core angle is around 6 degrees, and the best fit angle that we're viewing it is at around 7 degrees. So this gives a natural explanation for the lack of gamma rays in this source. Furthermore, from the modeling that we did, we constrained that the initial Lorentz factor is probably greater than around 9, which pretty much rules out a dirty fireball scenario, because most dirty fireballs have to have Lorentz factors less than around 10. So I will end off by also talking about the source size upper limit that we derived for AT2023 SVA. So the way that we did this was we utilized the radio light curve and the radio SED, where we found signs of strong interstellar scintillation being present. Now, interstellar scintillation is caused by small-scale inhomogeneities in the ISM that changes the phases of incoming wavefronts of radio sources. So when we think about GRBs, they are clearly cosmological sources, but these radio photons still need to travel through our galaxy and through the ISM to eventually get to us. Because the Earth's line of sight is changing with time to the source, this actually causes variations in flux due to electron scattering by these electrons in the ISM. And we can look at the degree of variation of the flux and use that to actually back out a source size upper limit, given the fact that if we have a source size that is greater than this upper limit, we wouldn't be able to see the variations that we see on the time scales that we do. So here we show the upper limit that we derived for AT2023 SVA, and also its comparison with respect to other Orphan afterglows and other classical GRBs that have ISS constraints. And what we find is that Orphan afterglows actually have statistically smaller source sizes when compared to the classical GRB population, for at least those that have ISS constraints. Now, it's important to note that this is a bit of a biased sample, as only the brightest GRBs, which well-sampled radio light curves, are able to have these ISS constraints measured. But the question arises as to what the reason for this is. And again, the question is, the answer is we really don't know yet. It could be due to intrinsic lower Lorentz factors in the jets of these Orphan afterglows due to them being possible dirty fireballs. It could be due to the fact that we're viewing them, most of them off-axis, similar to AT2023 SVA, and we're only catching the lower Lorentz factor moving material, but there's higher Lorentz factor moving material that is pointed away of us. Or it could be due to something else altogether, such as variations in the CSM density around Orphan afterglows, which would mean they possibly might have bigger mass loss history than the classical GRB population. So these are all just theories, and there are more theoretical and observational studies that need to be done for us to truly understand why this is the case. So I will end off with the 3 questions that I posed at the beginning of this talk. I hope I did a good job of answering them. And thank you for listening. And here is the paper, which has been accepted in Evan Ross and Press, so feel free to take a scan if you want to read it. Thank you.
So Gokul, your opening angle, the value that you derived, is very similar to 1 over gamma, right? It's not very different. And it also matches the opening angles of AGN jets that have similar Lorentz factors. So that makes a lot of sense. I don't know if in AGNs you see that they parallel as well, but it would be nice to check because you're getting answers quite similar.
Yeah, that would be really interesting if AGN also shows similar structure like that. Yeah.
Yes.
But is that consistent? You should have a lot more orphans than bright ones, is that true?
Yeah, we should. Yeah.
Okay.
But not a lot. I mean, you said that it's 1 degree extra. What?
Yeah, so from our modeling, we found is, I mean, within uncertainties, it still could be within the core, and there are some degeneracies in the modeling that always kind of happen, but our overall conclusion was that it's probably a little bit outside of the core opening angle, but not that much. So that's interesting because we would expect in that scenario, like, maybe we would still see some sort of gamma ray emission if we're like pretty close to the core, which it seems to be the case over here, but we don't see it. So it could point towards some difference in the population between these orphans and like the classical GRB population.
Is a cutoff?
Or there's a cutoff, yeah.
Yes, please.
So do you think most orphan afterglows are these off-jet observations, or like is there any sort of intuition about the distribution of what's causing these?
That's a good question. I definitely think some of them are. So I think some of them are definitely this off-axis situation, but we also have some situations, like Dan Perley put out a paper recently where one of his conclusions was that we could have a more moderately relativistic outflow that was actually accompanying the orphan afterglow. It doesn't necessarily have to be due to an off-axis situation. The thing is, there are a lot of degeneracies because for these orphan afterglows, we don't have good constraints on the explosion time because we don't have a GRB. So we usually just have like a non-detection, a detection, the explosion is sometime in between then. So if we can't constrain the rise time, we can't get a good constraint on the initial Lorentz factor, which is why there are like these degeneracies between the low Lorentz factor solution and off-axis solution and things like that. So I think the question is still, we need to understand more, yeah.
Okay, no more questions. Let's thank Gokul.
Okay, can you hear me okay? All right. Hi, everyone. My name is Cassie Lackas. I'm a Hubble and ITC fellow here at the CFA. And today what I want to tell you about is some of my very recent work looking at emission from the circumgalactic medium that can be affected by star formation feedback from the central galaxy. So I like to show this little cartoon when I'm sort of describing what the CGM is. But actually, I'm glad that I put it in here because there's the accreting gas streams that Avi was mentioning earlier that you can clearly see in this cartoon, which is these, oops, helps if I turn this on. So these accreting gas streams that we usually expect to come in sort of right along the major axis of the disk and connect in. So this is quite different from the accreting gas situation that Scott was telling us about earlier, where that might be a little bit more along the minor axis. But the nice thing about this cartoon is that it sort of picks out the different parts of the circumgalactic medium, the CGM, that we might be interested in. So there's that accreting gas, but we also have the outflows that come out along the minor axis of the disk. Some of those might recycle as well. And this region of space really encompasses all of the space surrounding that central galaxy. So as you can imagine, it can be very important for understanding how the galaxy at its center grows and evolves. So usually the way that we observe the CGM is in absorption towards a bright background light source. So we have some background source, usually a distant quasar, as it travels through the CGM of some foreground galaxy. Some of that light is absorbed, and that tells us the elements and the ions, the density, the temperature, and velocity of the gas there. But we only get that information along that one-dimensional line of sight through the CGM. So that's not terribly helpful. However, if we do this for a whole bunch of different galaxies where we have about one line of sight per galaxy, then we could make a plot like this, which shows the column density of, in this case, oxygen 6, as a function of impact parameter, this is how far away from that central galaxy the line of sight is. So what we could see is that there's actually a good amount of this ion, oxygen-6, in the circumgalactic medium of all of these galaxies on this plot. Each point here is a different galaxy. For both the star-forming galaxies in blue and even some of the passive non-star-forming galaxies in red. And then these open squares here are the non-detections. So we find a lot of this O6. We find it almost ubiquitously, but we really don't understand exactly what gas oxygen-6 is tracing. This is a pretty highly ionized ion, but it turns out you can get it in both hot and cold gas, depending on whether it's collisionally ionized or photoionized. We don't have a good constraint on that. And we also don't know whether it's tracing the inflowing gas or the outflowing gas or some more complicated sort of mixture of all of these things. And it's very hard to obtain that information from just this like one-dimensional line of sight through a given galaxy CGM. So this is where the sort of next generation of small telescopes comes in. There are many missions planned, or in various stages of planning and implementation, to try to observe the CGM in emission rather than just absorption towards a background light source. I'm just going to talk about one. This is the Aspera mission. This is a NASA Pioneer smallsat that will hopefully be launching in about a year from now. The PI is Carlos Vargas at University of Arizona. But the goal of this, it's a very small telescope. It has one goal, and that one goal is to look for oxygen-6 in emission towards just a handful, I think 3 or 4, nearby edge-on galaxies. So by looking at sort of above and below the plane of the edge-on galaxy disk, hopefully Aspera will be able to detect some O6. But this has never really been done before, so we don't really know what Aspera is going to be able to see or any of the other emission studies that are coming online soon. So what I've been doing is using the foggy simulations to make predictions for what we expect to see from this type of emission study. So on the left here, we have a video of one galaxy that is slowly evolving over time. It's oriented to be edge-on at all times. It sort of wobbles around a little bit, so if it looks wobbly, that's why. Just to try to keep it edge on. But the left is showing all of the gas, and the right is showing the oxygen-6 surface brightness. And they should be more or less synced up, so you can kind of tell that a lot of the gas streams that you sort of see in the background here, those don't really show up in oxygen-6. It's picking out sort of different structures. So one of the things that I've been doing is trying to understand sort of where do we see the strongest O6, and what type of gas is that actually tracing in the simulations. So if we pause this video just at redshift 0, so this is a sort of Milky Way-like galaxy right at redshift 0, again oriented edge-on, and then we ask ourselves how much of this O6 emission that we see in this image here would actually be detectable by something like Aspera. So for sort of a reasonable detection limit, everything in gray here is not detectable. So unfortunately, that is a very large part of the image. However, we are still able to detect these sort of small clumps of O6 in the densest regions very close to the galaxy. And we would expect this because emission scales as density squared. So these sort of small clouds that are the densest parts of the circumgalactic medium are probably going to be the parts that show up the most in oxygen-6. So the next question that I wanted to know is, what is this gas actually doing? We see that it's clumpy and it's close to the disk, but is it inflowing or outflowing? And so what this plot is showing us is a surface brightness profile of oxygen-6 as a function of distance out from the galaxy. So the galaxy center is down there at 0. This black line is just the full profile. You can see it sort of drops below the detection limit within about 20 kiloparsecs or so. But I've also split it up into inflowing gas in purple and outflowing gas in orange. And the nice thing about having a simulation is that we actually have this information that we may not necessarily have from the observations. And it's very clear that most of the oxygen-6 surface brightness is coming from the inflowing gas. However, if you remember the cartoon that I showed where the inflows looked like they were sort of coming in along the major axis, if I split up this surface brightness profile into major axis versus minor axis, all of these lines sit basically right on top of each other. So even though this gas is predominantly inflowing, it is not predominantly along the major axis. It doesn't really seem to have any sort of preferred orientation, which is a little bit strange. This is perhaps not exactly what we would expect for sort of classical gas accretion theories that predict it comes in along the major axis. So maybe instead this is picking up some of the HVCs that Scott was telling us about earlier. And in fact, we can see that too if we just come back to the movie briefly. A lot of the sort of clumpy structure that you can pick out by eye here is certainly not just along the major axis and inflowing streams. It's sort of chaotic and everywhere. So the next question that I was curious in was, can we figure out if there's some relation between what we see in the circumgalactic medium in terms of this O6 emission and any properties of that central galaxy? So I looked at a bunch of different properties. I looked at sort of the mass of the galaxy, the average density of the CGM and metallicity. This is the one that I think is the most interesting, which is how the oxygen-6 in the circumgalactic medium scales with the star formation rate of that central galaxy. So on this plot, we have 5 different galaxies. We have cute little names for each of them. These are the 5 simulated foggy galaxies. And each point here is a different snapshot in time from one of those galaxies. So I did this essentially just to get more data onto this plot, since we only have 5 galaxies. And as these galaxies evolve over time, they have different star formation rates at different times, and that allows me to populate this plot. But right away, you can tell there's a very clear positive correlation between the median oxygen-6 surface brightness within 20 kiloparsecs of the galaxy center and the star formation rate, where if the galaxy is forming stars more rapidly, it has much stronger, brighter oxygen-6 emission. You can also look at this a slightly different way, where instead of looking at the median brightness, we can look at what fraction of that 20 kiloparsec circle area has a brightness that's above the detection limit for something like Aspera. And that also has this positive correlation. So what we can see is that when the galaxy is forming stars more rapidly, it has both brighter and more widespread oxygen-6 emission in its sort of inner circumgalactic medium close to the galaxy. But we already know that this O6 is not tracing the outflows, so it's not tracing the feedback material that's being launched out of the galaxy. It's instead tracing the inflows. So this correlation could be indicating that it's actually tracing the fuel that will later become stars at some probably much later time, because again, this is very highly ionized and hot gas. And we can see this much more strongly as well if we look at one particular simulation, which is in the orange points down here, where I've turned off feedback entirely. So there's no outflows coming out of this galaxy at all, and you can immediately tell that it just completely drops the O6 surface brightness. So this is suggesting that this is pretty much just, there are no metals left in the CGM. When you turn off feedback, there are no outflows. It can't enrich the circumgalactic medium, so there's no oxygen there to be seen as oxygen-6. And we can see this, again, in videos with feedback on the left, the same simulation without any of the feedback on the right. And you can still see a little bit from that inflowing gas, but you really need that enrichment from the outflows, enriching the inflowing material with oxygen so that it can show up in oxygen-6. So by way of conclusion, I'll just say, what does this actually mean for Aspera and for other missions that will hopefully be coming up soon? We expect this emission to be close to the galaxy with a fairly clumpy morphology. And we expect that the more highly star-forming galaxies may have more oxygen-6 emission in their CGM, so this could affect the target selection for upcoming missions. And finally, because we have this simulation that can give us more information than what we could get from just observations, we can interpret the upcoming observations to tell us that perhaps the O6 is showing us where outflows and inflows are interacting and enriching and then flowing onto the galaxy. So I'll leave it there. Thank you. Yes. Yeah, so that's sort of the traditional way of observing the circumgalactic medium. That mostly just gives us column densities. So we get the column density of oxygen-6, and we get sort of the covering fraction, like how ubiquitous is it. And this is actually the reason why O6 was selected as the line to look at for Aspera, because it is the most commonly observed in those quasar absorption studies.
So you said the oxygen-6 is sort of coming from all over.
typically tracing isotropic stack?
Yeah, that's a great question. So as far as I can tell, the inflows are not fully isotropic. The bulk of the inflowing mass is in sort of these sort of large-scale filaments that don't have a preferred orientation, but are also not fully isotropic either. So I think the O6 is picking out only the inflowing material that happens to be isotropic.
Earlier, when you showed the figure of the detectability in Afterglow, there was a bubble-like looking things out far into the halo. I'm just curious what those were. Next slide. Next one. Yeah. So
There we go.
Up there, you got these little,
Oh, yeah, yeah.
obviously not a supernova, but hopefully.
These?
Yeah.
Yeah. So I think what those are, if I had to guess, I would say those are just clumps of gas that are either debris from a merger or was previously ejected or something like that, that have a little bit of oxygen in them. But you see sort of this bubble structure because it's only the outer shell of those that is highly ionized enough to show up in oxygen 6. So if you were to look at that in like a lower ion, it might not look like a bubble, it might just be a sphere.
Yes.
Yeah, it's a sort of a related question to one that I had before. So why specifically did you choose 06? But wouldn't it be easier to find, I mean, are there any easier tracers? I don't know, maybe MG2?
Yeah, that's a good question, absolutely. So I think the basic answer is no, this is the best possible tracer, because it is the most observed tracer for the circumgalactic medium. There have been a lot of studies that have looked at magnesium-2. That generally is not found as far away from galaxies. A lot of the magnesium-2 studies tend to find that much closer into the galaxy. So it just probes, more like the disk halo interface as opposed to like the CGM. So it could still be a good tracer, but just for a slightly different science goal.
And besides, we are made mostly of oxygen, our body mass. So we have a connection. Let's thank Cassie.